Okay, so we're looking at tangent planes and differentials and linearization in this section. And so if you have a tangent plane, it's very much similar to a tangent line, okay? The difference is I have a three-dimensional surface like a ball. And then if I choose one point on the ball and put a sheet of paper next to it, and it touches, the ball touches at that one point, then that plane is what we call a tangent plane. Okay, so that's what we have here. So we have a surface. All right, so our surface is z is equal to f of xy. So z is equal to f of xy. So at the point x naught, y naught, and z is f of x naught, y naught, we can find the tangent plane to the surface. Just like we could find the tangent line to a curve, we can find a tangent plane to a surface. So again, think of this as a sheet of paper. And think of this as a ball. It's a surface, and it's only going to touch that paper in one specific point. Okay, so we can define what the tangent plane looks like. All right, so here's the definition. So I want a definition. I want to let S be a surface. Defined by a differentiable function f of x, I'm sorry, z equal to f of xy. So if it's differentiable, I can find its partials. And let P naught, which is going to be x naught, y naught, z naught, all right, be any point on the domain of f. So be a point on the domain of f. Okay, that should be in the domain. I don't know why I said on. It should be in. And this should only be x naught, y naught, not z naught. So P naught is in the domain of f. Okay, then the equation of the tangent plane to the surface at the point P naught is z is equal to f of x naught, y naught plus f sub x at x naught, y naught times x minus x naught plus f sub y at x naught, y naught times y minus y naught. And sometimes you will see this written as just plain Z naught. Okay, so sometimes you will see f sub x at x naught, y naught. This is how I learned it, times x minus x naught plus f sub y at x naught, y naught times y minus y naught minus z minus z naught is equal to 0. So either way you can write it, that's the tangent plane. Okay. All right. So here's an example. Oh, let me explain it a little bit more. Okay. Actually, that's fine. Find the equation of the tangent plane to the curve when you're done. Z is equal to the square root of x squared plus y squared at the point P naught being 3 minus 4. Okay, so one of the things we need to do, this is easy, is find what Z naught is. So Z naught is the square root of 16 of 9 plus 16. So that's 5. Okay. All right, so now we need to find f sub x. So we're going to get 1/2 times x squared plus y squared to the negative 1/2 times 2x. Okay. And that is x over the square root of x squared plus y squared. And similarly, f sub y, after you do everything, you get y over the square root of x squared plus y squared. Okay, so f sub x at x naught, y naught. X was 3. So that's 3 over 5. And f sub y at x naught, y naught is negative 4 over 5. Okay, so therefore Z is equal to Z naught. Z naught was 5. Plus f sub x, which is 3/5 times x minus 3 minus 4/5 times x up y minus, I think it was a negative 4. Yeah. So therefore, I can multiply the whole thing through by 5, and I get 3x minus, oh, there's no 3x. 3x minus 9, and then I'm going to get minus 4y minus 16 plus minus z plus 5 equals 0. So we get 3x minus 4y minus z. I'm surprised I didn't simplify this. Negative 9 and negative 16 is negative 25 minus 20 is equal to 0. Okay, it's just that simple. Okay, so I'm gonna let you do this one. Find the equation of the tangent line, tangent plane. Ooh, girl, we slipped. Tangent plane to the hyperboloid z squared minus 2 x squared minus 2y squared minus 12 is equal to 0. So I may need to help you figure this out.
Yeah.
No, actually.
You do one more example, please.
I'll give it, yeah, I was getting ready to say this example uses something. See, this book is out of order. What do I mean by out of order? Normally, I teach something else before I teach tangent planes. All right, let's do the paraboloid. Z is equal to x squared plus 4y squared over 10. At x naught, y naught equal to 2, negative 2. Okay, so we need to find z naught. It's going to be negative 2 squared plus 4. Nope, this one's positive. Plus 4 times negative 2 squared over 10. So that's 4 plus 16 over 10. So that's 2. Okay. So now f sub x is going to bring 2 over 10 x, which is 1 over 5x. And then f sub y is going to be 8 over 10 y, which is equal to 4/5 y. So f sub x at 2, negative 2 is 2 over 5. And f sub y at 2, -2 is equal to -8/5. So therefore, I get z is equal to z naught, which was 2, plus f sub x, which is 2/5, times x minus x naught, which was 2, plus f sub y, which is -8/5, times y minus a -2. And when all is said and done, I get 2x multiplied by 5. So I get 2x minus 8y minus 5z minus 10 is equal to 0. So this is the tangent plane. Okay. All right, let's see here. Okay, so that's it for finding the equation of a tangent plane. There's really not much else that there is for that. Do you need any that's it. That's all that you do. Okay.
So you find z naught first.
Yeah, well, sometimes they'll give you z naught, but if they don't, you have to find it.
Okay.
Sometimes they'll give you z naught, sometimes they won't. Okay. All right, so linear approximation. Okay, so given a function, z equal to f of xy, with continuous partials, that exist at the point x naught, y naught, are p. All right, the linear approximation of f of x of f at the point x naught, y naught is given by the equation L of xy. Now this is the approximation, is equal to f at x naught, y naught. It's actually just taking the first part of the Taylor series in 2 dimensions of f sub x of x naught, y naught times x minus x naught. Oh, ooh, thank you. Plus f sub z, why in the world? F sub y of x naught, y naught times z, y minus y naught. Okay, so that's the linear approximation. So basically, what does that mean? So you remember from Calc 1 that Calc 1, I had this function that looked like this.
Oh, the linear approximation.
Yep. And so I had a function that went like this. And I know the value right here. I know this value. So I know the value at x naught. But I want to know what the value is here at x. Well, what you do is, what we used to do is the linearization literally is just finding the slope, finding the tangent line, saying this is the tangent line, okay? And its linear approximation is going to be the value that's real close, but it's linearized on the tangent line. And we have some error there because the true value is actually on the curve, but the linearization approximation comes off the tangent line. Well, we're doing the same thing. We're saying, okay, I know what the true value of the function is at that dot. That's x naught, y naught, z naught. I want to know what's the value of z if I move just a little bit away from there on the surface. So instead of trying to figure that out, I can linearize it and get the answer that is on the tangent plane and let that be an approximation to what I really want on the surface, because it's only going to be a little different. Because if it's tangent, it's coming off just ever so slightly at that point. So that's what we're doing. All right. What in the world? Oh, there it is. Okay. All right, so here's my example. Find the linearization of the function z equal to f of xy at the point, oh, yeah, at the point x naught, y naught, okay? And then find L of x, y about the point 3, 2. Oh, I should say about the given x naught, y naught. Okay, so in A, here's our function. Our function is z is equal to x squared minus xy plus 1/2 y squared. Okay, so the linearization, then we need f sub x, 2x minus y, and f sub y is negative x plus y. So we get L I think I need to give you a point. Three, two. Okay, so Z naught is going to be 3 squared, which is 9, minus 2 times 3 times 2 plus 1/2 of 4. So that is 13 minus 12, which is 1. Okay.
Wait, so for the Z naught, where did you get the 2 times 3 times 2 again?
Okay, so I put in 3 for X. So I got X3 for X. So that gave me X squared minus, oh, there's no 2. Wait a minute. Okay, because I'm looking at the second function of my example. Sorry. My second function has a 2. It has a 2xy. That's why. Thank you for asking. That's 3 minus 6. 13 minus 13. 7. Are we good now?
Yes.
Okay.
What happened? I can't hear anything. Wouldn't it be 5?
I don't know. I need I need to do it again. Okay. Girl, this one, Dr. Lott get tired. We got to work on this. Okay. 3 squared is 9 minus 6
plus 2
plus. Okay, there we go, 5. Okay, I agree with you. I did. All right, woo, now we got 5. Okay. Okay, so therefore L of xy is equal to 5 plus, oh, we got to figure out what f sub x is. F sub x at 3, 2 is 2 times 3 is 6 minus 2 is 4. And f sub y at 3, 2 is -1. So I get 5 minus 4 times x minus 3 minus y minus 2. Okay. So our linearized function is equal to 5 minus 4x plus 12 minus y plus 2. So L of xy is -4x minus y plus 19. All right. Minus 4x. So it should be L should be Z naught plus F sub x, which is 4. Oh, no, that's wrong. It should be F sub x. This is a 4. Okay. All right, so L naught Z naught plus F sub x at x naught y naught, which we said was 4. I'm okay with that. Times x minus x naught plus f sub y, which is indeed -1, times y minus y naught, which is -2. Okay, so now we get -4x minus y. So this now becomes -12. So I get -12 plus 7 is -5. Okay, that looks better. Okay, so basically, if you wanted to find, so you can find the error for a different small amount. So if we wanted to find what f of 3.2 is and 3.2.9 is, or something 2.1, then I could put it in this function and not have to put it in this other difficult function.
Okay, I was about to say, where did you get the -12 from? But it was distributed.
Yes, it got distributed. Okay, so technically, so let's see, f of 3.1, is it 3.1? 3.1, 1.9. 1.9 would be, let's see, so this is the true, so the true value is 3.1 squared, 3.1 times 3. Oh, I wrote 3.2. 3.1 times 3.1. That's 3.1 squared minus 3.1 times y, which is 1.9, plus 0.5 or 1/2, yeah, 0.5 times, and y squared would be 1.9 times 1.9. Okay, so now let's see what the linearization function gives us. So now we get L of 3.1, comma 1.9 is going to be -4 times 3.1 minus 1.9. I don't think this is going to be right. Plus 5. I'm going to say they don't look nothing like they're supposed to. Something is wrong. What did we do wrong? The function was x squared minus xy plus 1/2 y squared. Okay, so we did something hideously wrong. I just got to figure out what it is. Okay, f sub x, 2x minus y. When I plug in 3, I get 2 times 3 is 6, minus 2 is 4. I'm good with that. F sub y is -x plus y. I get -3 plus 2 is -1. Okay, so that's right. Z naught is 3 squared, which is 9, minus x times y, which is 6, plus 1/2 of y squared, 2, that's 5. Okay, so I agree with that. So that's the linear function. So the linear function is 5 plus 4 times x minus 3 plus -1 times y minus 2. So, oh, there we go. There we go. That's the problem right here. This is supposed to be a positive 4x when we changed it. Okay, there we go. I knew something was hideously wrong. Okay. Something's wrong because this is supposed to be close. This should be close to the answer. And it wasn't close. So that's how I knew something was wrong. Okay, so this is supposed to be a positive 4. still wrong. So we get 5 plus 4x minus 12 minus y plus 2. 4x minus y. 5 and 2 is 7. 7 minus 12, negative 5. So 4 times 3.1 minus 1.9 minus 5. Yay! There we go. The linearization is supposed to be close to the actual value. Okay, do you see that now?
Yes.
Okay, so the linearization is not too bad. It's off by 0.025. That's not bad. All right, so the true value of the function would have been this, but if we just use the linearized function, we get that. Okay, now I am okay in my spirit because that was not working for me. Okay. Do you understand that, or do I need to do another one?
It's okay.
You good?
Yeah, maybe one more.
Okay, one more. Okay. Okay, so I'm gonna give you the function f of x, y is equal to, ew, why would I do that to myself? Xy times the sine of xy about the 0.11 pi over 4. I had a nicer one, but I chose this one. Okay, so the first thing is, what is z? So z naught is going to be x, which is 1, times y, which is pi over 4, times the sine of pi over 4. So that's pi over 4 times the root of 2 over 2. So that's going to give me pi to root of 2 over 8. It's not cute, but that's what it is. Okay, so that's that. All right, so f sub x says, let's pull the y out and then do a product rule. So we get the first x times the derivative of the second, which is the cosine of xy times y, plus the second of xy times the derivative of the first. Oh, I forgot my first. The first times the derivative of the second, plus the second times the derivative of the first. So I get xy squared times the cosine of xy plus y times the sine of xy. What made me pick this problem? I must have been sick in the head. So f sub x at 1 pi over 4 is then pi squared over 16 times the root of 2 over 2 plus pi over 4 times the root of 2 over 2. So I can pull out a pi I can pull out an 8, and I can pull out a root of 2, and that leaves a pi over 4 plus 1. Okay. Then f sub y is actually the same thing, except the x's and y's are switched. So that's going to be x that's going to be x squared y, the cosine of xy, plus x times the sine of xy. Okay, so f sub y at 1 pi over 4 is going to be pi over 4. The cosine of pi over 4 is the root of 2 over 2, plus x is 1. So this is just going to be the root of 2 over 2. So I'm going to get the root of 2 over 2 times pi over 4 plus 1. Okay, not cute, but that's what it is. So L of xy, what was z? Z was pi, the root of 2 over 8. Pi, the root of 2. Uh-oh. That should be in the numerator. The root of 2 over 8 plus that first crazy thing. Uh-oh. The first, come on now. Thank you. Pi over 8, the root of 2 times pi over 4 plus 1 times x minus 1 plus the root of 2 over 2 times pi over 4 plus 1 times z, y, minus pi over 4. Okay, it's ugly, but you put in what you get. Okay, we got this for z naught. Where is it? We got this for z naught. So that's what goes in here. And we got f sub x. Where's f sub x? We got this. So that's what goes in there. And then we got f sub y. And that's what goes in there. Okay, that's it. Okay. I'm trying to think, do they talk about differentials? I don't see where they talk about differentials. Oh, there we go, differentials. Okay. All right, so let's, I got 3 minutes. I can squeeze this definition in here. Okay, differentials. All right, so recall, all right, that the equation of the tangent plane all right, to the curve z is equal to f of xy is given by, now I'm going to write it the way is given by z is equal to z naught plus f sub x at x naught y naught times x minus x naught plus f sub z, f sub y, oh my gosh. That comes from the fact that my student is doing research and we're using the variables x and z. So everything, my brain wants to do z's instead of y's. Okay. All right, so we're going to let z equal, well, z is equal to f of y. Okay. So we're going to let df, by definition, is going to be the partial of f with respect to x. So f sub x at x naught, f sub x times dx plus f sub y times dy. So this is the differential. Notice this little piece right here, I'm calling dx. And this little piece right here, I'm calling dy. And so that's what z, how z differs from z naught. Okay. So that's the differential. So nice and easy. Example. F of x, y is equal to x e to the y plus y e to the x. So f sub x is equal to e to the y plus y e to the x. And f sub y is equal to x e to the y plus e to the x. So the differential df is going to be e to the y plus y e to the x dx plus x e to the y
Wait, what happened? You're on mute.
my Zoom just went out. So for some reason it's recording. Okay. Let me see. I told it to stop recording. So I don't know if this is